Hey class, and welcome back. I'm really bummed that I can't be with you all today, but I thought I would go ahead and make this video so that we can continue with our material and you guys will have some of the things you need in order to do your first homework. On that topic, here's a few reminders for you all. The first homework is going to be due at the start of class Friday, the one I handed out in class last time, so make sure you do that. If for some reason you miss a class, you can also find the first homework assignment on Foxtail. Don't forget your other assignment for this week is to stop by my office sometime. I think I've seen about half of you, so make sure the other half of you come on by sometime this week. And then don't forget that you have a pre-lab due at the start of lab on Thursday, which if you're watching this on Wednesday, as you should, is due tomorrow. All right, so what I want to do now as we jump into looking at the physics and describing how the world around us works, first I want to give us all some of the same basics with looking at units and units of measurement. So throughout the course of the semester, we're going to be looking at various different things, measuring lots of different things about the world around us, whether we're talking about accelerations, gravity, forces, velocity, energy, work, momentum, inertia, all kinds of different cool physics concepts. And as we do, we're going to describe them not only using numbers or amounts or magnitudes, but we also need units to go along with it. For example, going for a walk the distance of 100 yards is not the same as going for a walk a distance of 100 miles or even 100 feet. And so we need to make sure we pay close attention to our units and the different types of units we use. So in this class, we're going to mostly use SI units, or the European style of units, and we're going to use what we call base units, which are the kind of main fundamental units, and then other things that are based off of that. I'll give you some examples here in a minute. So the base units include the base unit for units of measurement of length, which are meters, units of mass, which are kilograms, the unit for time we'll use is seconds, and then for temperature is Kelvin. And believe it or not, the vast majority of everything that we deal with this semester will be built off of these base units. So think, for example, about something like velocity or a measurement of speed. It's just miles per hour is what you might be used to in a car, or for the SI units, meters per second. It's a distance, meters, divided by a time, seconds. So it's based off of these units, and you can see why they're called base units since it's based off of those. So other things like velocity, acceleration, even the force units of newtons are actually based on kilograms, meters, and seconds all combined. So be prepared to deal with all of those in a lot of different ways. So as we use these measurements, or excuse me, these units, we're going to be using them to take different measurements. Throughout lab, in order to do the scientific process, we need to take measurements, and to understand the physical world around us, we have to use measurements all the time. And this is something you're used to doing, right? You've probably measured your height, your weight, maybe you've looked at your watch to make sure you get to physics on time because no one would want to be late to physics class. You might have taken your temperature, or something I've been doing lately. I've taken the temperature of my house a lot because I've been trying to make bread, and the way in which the bread rises is dependent on the temperature. So I check to see what the temperature is at different places in my room. And you might do things, you go to the grocery store, weigh a cantaloupe. I don't know why I chose a cantaloupe. It's a weird fruit, but it's a good fruit, but it's kind of an odd one, not one you buy all the time. Maybe you weigh a bunch of apples. Or lately, with my baking, I've been baking based off of masses, and so I use different weights all the time in the kitchen. So you're used to taking measurements, and there's different tools to do that, whether it's a scale, a meter stick, a tape measure, a thermometer. We have different tools to take these measurements. All right, the next thing I want to talk about is the idea of scientific notation. So you might be familiar with scientific notation. It's not uncommon for, in day-to-day life, to come across things that need to be expressed with very large or very small numbers. If we're talking about things like the distance between us and the moon, or if you're talking about, maybe the amount of time there is in somebody's lifetime, and you want to talk about it in terms of seconds, it's going to be a lot of seconds. Talking about things that are small, like the mass of cells, very small, even the size, you check out my hair. See how thin this is? Yeah, you probably can't tell on the video, but it has a very small diameter. So if you're dealing with things that are very large or very small, it's not convenient to write out these really numbers with tons of zeros. You might miss one, or it just takes up a lot of space. And so in order to write them more conveniently and express them in a more organized manner, we use what's known as scientific notation. So just to remind you, scientific notation is used for large or small numbers, and what it is it's always going to be some number known as a coefficient. In this case, we're taking the number 0.000008 meters and writing it in scientific notation. So your coefficient is going to become 8, and you're going to multiply that by a power of 10. In this case, the power of 10 would be 10 to the negative 6th power. And so writing this very small number becomes more convenient as being written as just 8 times 10 to the negative 6th power. All right, to write a large number, you can do the same thing, but your power of 10 will now be positive. So if you have 2,500,000 seconds, you can instead express that as 2.5 multiplied by 10 to the 6th power seconds. So if you wonder how I got to these, I got to them using these powers of 10. And keeping in mind, so if you take 10 and multiply by 10, that gives you 100. That's 10 to the 2nd power. If you take 10 times 10 times 10, that's 3 tens, so 10 to the 3rd power. 10 times 10 times 10 times 10, 10,000, 10 to the 4th power, and so on. So as we see in this last one, when we had 2.5 million seconds, 10 to the 6th power represents 1 million, and so we took 2.5 and multiplied it by 1 million in order to give us 2.5 million seconds. So right here, these are both identical numbers, just written in different forms. Kind of the idea of having 12 eggs or a dozen eggs. You have the same number of eggs either way, you're just writing it in 2 different formats. And again, we care about powers of 10 because we see them all throughout science, whether you're dealing with something as large as a galaxy, which is measured on the units of meters at 10 to the 21st power meters, or something super, super small like an atomic nucleus, which would be measured at 10 to the negative 14th power meters. That's how tiny a atomic nucleus is. So how do we arrive at these exact scientific notation values? So keep in mind it's always the coefficient multiplied by a power of 10. Positive power 10 if it's a number greater than 1, negative power of 10 if it's smaller. All right, and the way that you figure out the power of 10 is by the way you move the decimal place when going from the normal number to the scientific notation. So if you had, again, a normal number like 52,000, if you take your decimal place and you move it to the left, you're going to move it 1, 2, 3, 4 spaces in order to get a coefficient of 5.2, and so it would be 5.2 times 10 to the 4th power. So you notice you could go 1, 2, 3 places, and then you'd have 52 times 10 to the 3rd power. Or you could go 2 places, 520 times 10 to the 2nd power, and so on. But in order to have proper scientific notation, your coefficient should always be between 1 and 10. So it should be a single-digit number, sometimes with decimals as well, but it's always between 1 and 10. And so for the small number here, we count moving the decimal place 1, 2, after we've moved it 3 times to the right, we have a coefficient of 3.78, that's between 1 and 10, check, and times 10 to the negative 3rd power. So I want you to actually practice this. Here's 3 numbers, some of which are big, some of which are just normal everyday numbers, but I want you to practice. Pause the video, write each of these in scientific notation. Ready, go. All right, hopefully you all did that. The first one, we have 12,800,000 meters, which is the diameter of the Earth. You take that and you can count. Move the decimal 1, 2, 3, 4, 5, 6, 7. So we should have 1.28 times 10 to the 7th power meters. Here for kilograms, to move the decimal place, 68 kilograms, you just have to move it 1 place. 6.8 times 10 to the 1st power kilograms. And for the hummingbird, 1, 2, 3, so 2 times 10 to the negative 3rd power kilograms. One other thing that you can do, and you'll get to practice on the homework a little bit, is writing numbers. Instead of using powers of 10, you can replace them with metric prefixes. All right, so these metric prefixes, things you might be familiar with like giga, mega, or like terabytes even, those really are just letters and words, prefixes, that replace or represent powers of 10. So you could have 1,000 grams, or 1 times 10 to the 3rd power grams, or you can replace that 10 to the third with kilo and just say it's the same as 1 kilogram. All right, so when you have a hard drive or a USB drive with 3 gigabytes of storage, that means you have 3 billion bytes, or 3 times 10 to the 9th power bytes. But instead of saying 3 times 10 to the 9th power bytes, we just replace the times 10 to the 9th with giga and say it's 3 gigabytes. All right, and the same thing can go with small things as well. The human hair has a diameter of, let's say maybe something on the order of like 8 nanometers, or 8 times 10 to the negative 9th meters. All right, so keep that in mind. And the homework, I asked you to take a big number or small number, write it scientific notation, and then again using a metric prefix instead of the power of 10 before finally guessing what the measurements are. All right, so let's practice this a little bit. Here's a number, the distance to the moon from the Earth on average. It's 384 million meters. So to write this in proper scientific notation, you can even pause, try it out, but what you should get is 3.84 times 10 to the 8th power meters. Now, if you wanted to write that using a proper metric prefix, you can look in tables or online and you see there is no metric prefix for 10 to the 8th power. So shoot, you feel stuck. Well, now you need to move the decimal place either additional places forward or additional places back in order to get it into a power of 10 that is represented by one of the metric prefixes. So 8 is nearest to 9, so I would just move the decimal one more place, giving us an improper, not proper scientific notation value of 0.384 times 10 to the 9th power meters, and now you can replace times 10 to the 9th with a metric prefix, and you get 0.384 gigameters. You could have also done the opposite, gone from 8, not the opposite, but the other direction, gone from the 8th power to the 6th. So if you move the decimal back 2 locations, you could have got 384 times 10 to the 6th power meters, or 384 megameters. All of those are same ways of representing this. So you can represent the distance to the moon like this, you can represent it here, you can represent it here, or you can represent it as 0.384 gigameters or even 384 megameters. All of those are equally accurate ways to represent the same value. Now let's do a small value and do the same thing. So here we have the length of the pox virus responsible for chicken pox, a very small number of centimeters. So first we write it in proper scientific notation. We count moving the decimal place 7 places, and we get 3 times 10 to the negative 7th power centimeters. Now we have a problem. We already have a metric prefix here, centi, which represents times 10 to the negative 2nd power. So first we need to take out the centi and add that negative 2 power to our existing negative 7 power, making it 3 times 10 to the negative 9th meters. And now we can replace 10 to the negative 9th with the metric prefix of nano. So the length of the pox virus is 3 nanometers. Hey class, so the next thing that I'd like to talk about is unit conversions. So there's oftentimes we're going to be dealing with different types of units. So for example, like I gave it, I think an example earlier, say you had like 4 dozen eggs and you wanted to figure out how many overall total eggs you had, you'd have to convert from dozen to individual eggs. Or if you were driving in your car, you look down at your speedometer, it says you're going 75 miles, okay, maybe, hopefully not, maybe you're going 35 miles an hour, and you wanted to do some calculations using the SI units we've been learning about with meters and seconds. You'd have to convert to meters and seconds in order for the calculation to be possible. So what I want to do is I want to show you how we do this, the kind of pattern or strategy for doing unit conversions. And what you're going to be doing is taking various values and changing their units. So let's look at an example, because I think the easiest way to go through this process is learn by doing. So let's say you're somewhere, going off the example I mentioned earlier, where you see a speed limit sign and it says the speed limit is 65 miles an hour. You've been taking physics, you learned that to think in terms of meters per second. So let's go ahead and see how can we convert 65 miles an hour and determine how many meters per second it is. Well, what you're going to need to do is you're going to change the miles into meters and your hours into seconds. And so I don't know exactly how many meters there are in 1 mile, but I do know that 1 mile is equal to 5,280 feet, and we know that 1 meter is equal to 3.281 feet. So we can use those as conversion factors in order to change our units. So the way that you do this is all you're really doing is you're taking that initial units that you have, initial value, and you're not changing it. You're keeping it the same by multiplying it by 1. And when you multiply it by 1, its value doesn't change, but that 1 that you're multiplying it by is what's known as a conversion factor. So you see here, we're taking our 65 miles an hour and multiplying it by 1 twice. So again, we're not changing the value because anything times 1 is still itself. And so we're taking 65 miles an hour. The first 1, the first conversion factor that we're going to multiply it by is the fact that there's 5,280 feet in 1 mile. So since the top and bottom of this fraction are the same, this really just has a value of 1. So that enables us to convert from miles, since they're on top and bottom, they'll cancel out, and go to feet. Next, let's go ahead and go from hours to seconds. Since our 1 hour down here is on the bottom, now we put hour on top, and we need seconds on the bottom. So we'll take and multiply by 1 hour and divide by 3,600 seconds that are in 1 hour. So 65 times 5,280 feet divided by 3,600 seconds gives us 95 feet per second. But we're not done yet. We need to multiply by 1 more time in order to go from meters to feet. So now, again, since we have feet on top, we have to put feet on bottom. We'll multiply by this conversion factor, which again is equal to 1, since the top and bottom are equal values, just with different units. So we take our 95 feet per second, we divide by 3.128 feet, and we get 29 meters per second. So in case you're confused, when you see these conversion factors, everything on top is multiplied together. So really you're taking 65 times 5,280 times 1 times 1, and then dividing by 3,600 and 3.281. And so you end up getting 29 meters per second as the overall velocity. So now I want you to try another one. Here's one where I want you to convert the airplane speed. An average airplane might be moving at somewhere in the ballpark of 2,330 kilometers per hour, and I want you to tell me what it is in meters per second. So pause the video and try it out. Ready, go. Did you try it? I hope so. So again, you're taking that initial value of 2,330 kilometers per hour and you're multiplying it by 1 2 times. First, a conversion factor to go from kilometers to meters, and then another one to go from hours to seconds. You do the math, and you should have gotten 647 meters per second. Pretty fast when you're moving in an airplane. All right, so that wraps up kind of the introductory things that I wanted to give you, kind of the pre-Chapter 1 material for the class. And now I just want to give you the briefest introduction to this first chapter where we're going to investigate Newton's laws of motion. Now keep in mind, these are the fundamentals of physics that we're going to be using all semester long. So if any of this stuff ended up confusing you, come with questions and we can discuss them and unpack them in class on Friday. All right, so the way I organize these chapters, each one is based around some day-to-day life activity. This first one is using ice skating as sort of the physics of everyday life example. And I like to start with questions to think about. So here's a few questions for you to think about. Things like, why does a stationary ice skater remain stationary? Okay, that's kind of a silly question, but they don't start moving spontaneously. I wonder why. Okay, what physics might be involved? Why does someone who's moving on ice skates just keep moving and not stop? Sometimes they do stop, though. How do they stop? What makes them stop? So let's talk about the physics of these. These questions, because at the very beginning of the semester, they're like kind of boring a little bit sounding. But as we get into the term, we're going to unpack questions that are more and more complicated and more interesting. So let's take these one at a time. First of all, why is it that everything in nature tends to stay stationary, to just remain at rest if it's not acted on by some outside influence? Do you have any idea what physics principles might be behind this idea? Well, there is a physics principle, and it's what's known as inertia. All right? Hopefully you guys can understand inertia well, because we're going to be talking about it all semester long. It's a really integral and important aspect of nature. Things with mass have inertia, which means objects that are at rest want to stay at rest. All right? It also means, as we'll talk about here in a minute, that objects, once they're moving, want to keep moving. This is known as inertia. Show you a cool video here. This is a great video. You can check out the whole thing. I'm just going to show you a small clip of part of this video, which shows you some pretty neat examples of inertia. All right? So there's some all kinds of different cool parts of this, but let's just fast forward here. Some neat slow motion videos. So for example, here's a watermelon being shot by a bullet. Check it out. Even though it gets hit by a bullet, it explodes outward in both directions because its overall inertia makes it want to stay put. Or this one's just wild. This guy has pretty good aim, and he slices this tomato with his sword. And check it out. It cuts through it, impacts the tomato, but the tomato stays put. The top and the bottom do not move hardly at all relative to one another because they have inertia. They have a desire, a tendency to stay in place, to stay at rest. And so as I mentioned a minute ago, things in motion also want to continue in motion. If you roll a ball, it's going to keep rolling for a long time until eventually friction and air resistance slow it down. If you get going on ice, or if you push a hockey puck across the ice, it's going to keep sliding for a long period of time before eventually coming to rest. Why is that? It's the same reason. Things that are in motion want to stay in motion. They have inertia. So anything with mass naturally resists a change in motion. And that fact is what's known as inertia. And that fact is actually summarized by Newton's first law of motion. He tells us that anything free of external influences will continue to move in a straight line, covering equal distance in equal amount of time. Things have inertia, and they resist a change in motion. And we see this all throughout the natural world, and it's really, really important to understand. You're going to see it pop up as we talk about Newton's laws. We're going to see it pop up. It helps to explain how, for example, you're able to stay in your seat when you go upside down in a roller coaster. It's an important idea that applies in many different ways. So that's Newton's first law of motion. Objects have inertia. They resist a change in motion. We're going to build off of here on Friday, but I wanted to get you guys thinking about inertia as it helps with the homework. And I'm going to stop the video now, and we'll continue on with more information next class. Have a box-worthy day.